These are the notes for AP Calculus on the topic of relative, also called local extrema for special functions. So let's first take a look at trig functions. So it says state the increasing and decreasing intervals of the function, then find the x-coordinates of all local extrema, and identify each as a local maximum or a local minimum. So the first thing we need is to find our critical numbers by taking the first derivative. So f prime of x is equal. Since these are added, you can take the derivative of each one separately. The derivative of cosine is negative sine x. And then remember this one, sine squared can also be written this way. And if you write it that way, it's easier to see that you have to use the chain rule because you have a function inside there. So on the outside, you'd be using the power rule. So it'd be plus 2, and the function inside stays the same. Sine x now just to the first power. But then the chain rule says you have to also multiply by the derivative inside. So the derivative of sine x is cosine x. Now on this one, you can see sine and cosine are defined everywhere, so this will never be undefined. So we're just, remember the critical numbers over the first derivative is either 0 or undefined. So here we're just going to be looking for what makes the first derivative 0. And to help us solve this, what we can use is factoring. We can factor out a sine of x. So we'd have sine of x, and then what we'll be left with, first term will have a negative 1. And then plus, second term will have a 2 and cosine x left. So now in this factored form, one of these would have to equal 0. So either, to multiply to be 0, one of them has to be 0. So either sine of x would have to be 0, or negative 1 plus 2 cosine x has to be 0. So let's start where sine is 0. Well, if you think on your unit circle, notice the interval is from 0 to 2 pi. So where sine is 0 is right here at 0, which is also 2 pi. The coordinates are 1, 0. Remember, sine is the y-coordinate. And also over here on the unit circle, coordinates at that point are negative 1, 0, given sine is the y-coordinate, so that's at pi. So that'd be at 0, pi, and 2 pi. Those would be our three critical numbers from sine of x being 0. But then we could also have negative 1 plus 2 cosine x equals 0. So if you isolate the cosine, it'll make it easier to solve. By adding the 1 and dividing by 2, you're looking for where cosine is 1/2. And recall cosine is the adjacent over the hypotenuse. So let's go ahead and figure out where the adjacent over the hypotenuse would be positive 1/2. So there's the adjacent 1, hypotenuse 2. See, this would be root 3, so this is the angle pi over 3, 60 degrees. And it's also in this quadrant right here. Adjacent is 1, hypotenuse is 2. So this would be 2 pi, which is 6 pi over 3. So that means this would be pi over 3 less than it, so 5 pi over 3. So those would be our other two critical numbers. X equals pi over 3 and 5 pi over 3. So let's put all those on our number line. And this time we're looking just between 0 and 2 pi. So put the 0 with a bracket on that end, and a 2 pi with a bracket on that end to remind yourself we're not going to negative infinity and positive infinity in this case. And let's just put our critical numbers in order on the number line. So if we go counterclockwise, starting with 0, 0 is already on there, it's an end point. The next one we hit is pi over 3. And then after pi over 3, the next one we hit is pi. And after pi, the next one we hit is 5 pi over 3. And then we have 2 pi, which is another endpoint. And then label your number line. This is the first derivative test, so it's f prime of x. So all of these, including the endpoints, which are also critical numbers in this case, make the first derivative equal to 0. And then we just have to find something to test on each of these intervals to see whether the derivative is positive or negative. So between 0 and pi over 3, you could use pi over 6, probably your easiest choice, without a calculator. Notice you can't test 0 here because 0 is also a critical number. So you test pi over 6. Well, pi over 6 would be right there. Already got a circle. And so let's plug it into the factor form. It's probably the easiest to tell if it's positive or negative. So sine pi over 6, that's positive. Everything's positive in that quadrant. Cosine is root 3 over 2. So if you plug in root 3 over 2 for cosine, notice what's going to happen is the 2's reduce out, and we'd be left with negative 1 plus root 3. So negative 1 plus root 3, square root of 3 is a little bigger than 1, so that's going to end up being positive. So positive times a positive, positive on that. Then between pi over 3 and pi, the easiest thing to test there would probably be pi over 2. So pi over 2, we don't have to draw a triangle, it's right up here at the top. And the coordinates there is 0, 1, and sine is positive 1, so sine is positive. Cosine is 0, so that's going to wipe this term out. You'll just be left with a negative term. So that'll be a negative 1. So positive times a negative, that's going to be negative. In between pi and 5 pi over 3, probably the easiest thing to test would be 3 pi over 2. And there you don't have to draw the triangle, it's just at the bottom there. The coordinates 0, negative 1. So sine, there is a negative 1. And cosine is 0 again. So that's just leaves you with a negative 1. Negative times a negative is positive. And finally, between 5 pi over 3 and 2 pi, you could choose pi over 11 pi over 6. Let's use pi over 6 here. Or you can use 7 pi over 4 also. So let's use 11 pi over 6. Since we already used pi over 6. Right here. Negative 1, 2, and root 3. So let's see, the sine of 11 pi over 6 right there would be opposite over hypotenuse, so negative 1/2, so that's going to be negative. And the cosine there would be root 3 over 2. So when we plugged in root 3 over 2, the 2's reduced out, and we were left with just a root 3, so negative 1 plus root 3, remember square root of 3 is between 1 and 2, that's like 1.7. Negative 1 plus 1.7, that would be positive. So negative times a positive would be negative. So what this shows us is the original function, f of x, is increasing when the first derivative is positive and decreasing when the first derivative is negative, and back to increasing, and then back to decreasing. So we can answer the first part of the question, but it says state the increasing and decreasing intervals in the function. So we can say f is increasing on interval from 0 to pi over 3, and then also from pi to 5 pi over 3. And we can say f is decreasing on the interval from pi over 3 to pi, there, and a u for union, also with on the interval from 5 pi over 3 to 2 pi. So that answers the first part of our question. And we're also asked to find the x-coordinates of all local extremities. So let's look at our critical numbers and see if they actually were local mids and maxes or not. So at pi over 3, notice the first derivative changes from positive to negative, so that's a relative or local maximum. So the graph goes from increasing to decreasing. And at pi, the first derivative changes from negative to positive, decreasing to increasing, that's a relative or local minimum. And at 5 pi over 3, the first derivative changes from positive to negative, goes increasing to decreasing, so again, that's a relative maximum. And it only asks for the x-coordinates, so we don't have to plug it back in the original equation to find the y-coordinates. So we can say f as relative maximums at x equals pi over 3 and x equals 5 pi over 3. And we can say f has a relative minimum at x equals pi. Okay, let's take a look at one more example that's slightly more complicated in some ways than this one, but also deals with trig functions. So here we've got 2 secant of x plus tangent x, and again on the interval from 0 to 2 pi. So let's first find the critical numbers by taking the derivative. So again, we've got plus here, so we can take the derivative of each one separately. The derivative of secant of x, so 2 just stays out in front, is just secant of x times the tangent of x, plus the derivative of tangent of x is the secant of x squared. So we can simplify this by factoring out the GCF of secant x. Now I'll leave us with 2 tangent x plus secant of x. Now it's completely factored. However, if you leave it like this, the secant of x, it won't be too hard to figure out where that's 0 and defined. But here we've got 2 tangent x plus secant x. If we leave it in this form, it's going to be kind of tough to tell where that's 0 and undefined. So one technique that you can use that can, on certain problems like this, can make it easier to find your critical numbers is remember all the other 4 trig functions can be written in terms of sine and cosine. So let's see what happens when we switch everything to sine and cosine. So secant of x, remember that's the reciprocal of cosine. So that's 1 over cosine of x. And then tangent of x, remember we can write tangent as sine over cosine. The 2 just stays on the numerator there. So 2 sine of x over cosine x. Plus, there's another secant of x, which again is 1 over cosine of x. Now let's see what we can do to make that simpler. So we've got 1 over cosine x on the outside. And notice these are fractions, but they have a common denominator of cosine, so we can combine it to be one fraction. So it'd be 2 sine of x plus 1 over cosine x. And then we can multiply the cosine x's together on the denominator. So on the numerator we'll just have 2 sine of x plus 1 over on the denominator cosine of x times cosine x is cosine of x squared. And then it's easier to find your critical numbers by saying the numerator equals 0 and the denominator equal to 0. So if we set the numerator equal to 0, 2 sine of x plus 1. And then we'll also set the denominator equal to 0. So this one, over the critical numbers over the derivative is either 0, coming from the numerator, or undefined, coming from the denominator. So when you solve this one, you first isolate the sine of x. So the sine of x, if you subtract 1 divided by 2, would be negative 1/2. So remember, sine is the opposite over the hypotenuse. So let's try to figure out where that would be on the interval from 0 to 2 pi. So the opposite, hypotenuse is always positive here, so the opposite would have to be negative 1. So that would be right down here, minus 2. And that's an angle of pi over 6 in there. This is pi, which is 6 pi over 6, so this would be 7 pi over 6. And also, in this quadrant right here, we have negative 1 over 2, so that would be 11 pi over 6. So those are our two critical numbers that make the numerator 0, from 2 sine of x plus 1 equals 0, so equals 7 pi over 6. 11 pi over 6. Now let's look at where cosine is 0. That's a little bit easier. You can't draw a triangle 0 here. So remember cosine, it's going to be one of these 4 points here, or one or more of those points. It's got to be the x-coordinate. Remember, cosine represents the x-coordinate, so the x-coordinate 0 is right here, 0, 1, and right here, that's 1, 0, negative 1. So on the unit circle, that's pi over 2 and 3 pi over 2. And we live between 0 and 2 pi. So those would be our other two critical numbers, pi over 2 and 3 pi over 2. So again, let's draw this out in number line. Again, we're looking from 0 to 2 pi. So let me move this down a little bit so a little more to work with. From 0 to 2 pi, and we'll label it f prime of x. Again, this is the first derivative test. Our critical numbers in order. The first one we hit is pi over 2. Okay. And the next one we hit in the unit circle is 7 pi over 6. And the next one we hit is 3 pi over 2. And finally, we get 11 pi over 6 before we get to 2 pi. All right, so this time though, remember 7 pi over 6 and 11 pi over 6, those made the numerator of the derivative 0. So those made it 0. That's 7 pi over 6, 0, and 11 pi over 6. However, pi over 2 and 3 pi over 2 came from cosine equaling 0, and that was on the denominator. So those two x values make the derivative undefined. They came from making the denominator 0. All right, let's see what we can test on this one. Now, on this one, notice 0 and 2 pi, unlike the previous problem, are not critical numbers, which actually makes it easier. That means you could actually test 0 on this first interval if you want to. So if you test 0 right here. Okay. Now, let's test in our derivative. And notice there's a little shortcut we can use on this one. We've got a squared there, right? Even exponent. So that tells us the denominator is never going to be negative. So we don't have to worry about testing the denominator. It won't be negative anyway. So really all we have to do is test into our numerator, 2 sine of x plus 1, to see if that's positive. Well, sine right there is 0. So that wipes that out. So you just end up with positive 1 there. That's positive on 0. Between pi over 2 and 7 pi over 6, probably the easiest thing to test would be pi. You test pi, that's right over here on the unit circle. That's negative 1 and 0. Again, the sign there is 0, so you're just left with positive 1, so again, it's positive. Now you've got kind of a small interval here, 7 pi over 6 to 3 pi over 2. What can we test on that interval? Well, there, you have a couple options there. Probably the easiest one to test would be, well, you could test either one there. Let's say we test, let's see, that's 5 pi over 4. Would be in between those. We can also use 4 pi over 3. So this would be negative 1, and root 2. And the sign there is negative 1 over root 2, which is the same as negative root 2 over 2. So if we put negative root 2 over 2, you can see what would happen there is the 2's would reduce out, and we'd be left with negative root 2 plus 1. And square root of 2 is between 1 and 2, it's like 1.3 or something. So negative 1.3 plus 1, that's going to be negative. And then between 3 pi over 2 and 11 pi over 6, we can also use a similar one. We can use 7 pi over 4. And notice the sign there is also negative 1/2. I'm sorry, negative root 2. Negative 1 over root 2. So again, it's still negative root 2 over 2, so we get the exact same thing that we got when we plugged in 5 pi over 4, and again, it's negative. The sign is the exact same value there. And over here, since 2 pi is not a critical number, we can also actually test 2 pi. So we test 2 pi. Notice that's really the same as testing 0. It's the same place as your circle, so sine of 2 pi is also 0 plus 1 positive. So this shows us where our original function f of x, when the first order is positive, function will be increasing, still positive increasing, and then negative would be decreasing, still negative decreasing, and then positive increasing. So we can answer the first part of the question where f is increasing and decreasing in intervals. F is increasing. Let's talk about intervals based on. Now here, normally I put a parentheses, but notice 0 was not a critical number here. So that's part of our interval, 0 actually made it positive. That's what we tested. So here you would actually use 0 with a bracket. And even though it doesn't change sign, because it's undefined there, we do need to stop at pi over 2. And then we can start at pi over 2 to 7 pi over 6. And then there's another interval where it increases, so u from 11 pi over 6 to 2 pi. Again, 2 pi is not a critical number like the last one, so that's actually what we tested. That does make the derivative positive, so actually we put a bracket up there. And then f is decreasing on 7 pi over 6 and 3 pi over 2. It's undefined, so to stop there, and then between 3 pi over 2 and 11 pi over 6. Now let's find our critical numbers if there are local mins, local maxes are needed. So let's start at pi over 2. Notice the first derivative doesn't change sign there, so pi over 2 is not a relative min or max. At 7 pi over 6, the first derivative f prime changes from positive to negative, so that's a relative maximum. That's from increasing to decreasing. At 3 pi over 2, again, the sign doesn't change, so it's not a relative min or max. And at 11 pi over 6, first derivative changes from negative to positive, so that's a relative minimum. Goes from decreasing to increasing. So we only ask for the exponents, so we can say f as a relative maximum at x equals 7 pi over 6, and f has a relative minimum at x equals 11 pi over 6. Now, one other thing to be careful to point out on these problems here is the undefined places. Now, here we knew they weren't critical numbers, they weren't relative mins or maxes because this first derivative didn't change sign. But even if the first derivative had changed sign, in this particular problem, these would not have been relative mins or maxes. And the reason why is if you think about where pi over 2 and 3 pi over 2, if you plug it back to the original function, remember sine of pi over 2, look right here, tangent of pi over 2, I should say. Tangent of pi over 2 is sine over cosine, 1 over 0 would be undefined. And secant is actually undefined also, because cosine is 0 and the reciprocal of 0 is undefined. So, in the original graph, there's actually vertical asymptotes at pi over 2, and the same thing happens at 3 pi over 2. So, even if these had switched sign because of the vertical asymptote, that means the function is not continuous there, so these could not be relative to maxes in this particular problem. So what this would look like roughly, if you do a rough sketch of this, we've got vertical asymptotes here, pi over 2 and 3 pi over 2. So notice we've got the function is increasing. So just a rough sketch from left to right here would be increasing until there. Then it's increasing and decreasing. Increasing and decreasing. And then it's decreasing and then increasing. So something like that. That's what we would see. Okay, now let's take a look at trig functions. Take a look at another special type of function. That's piecewise functions. So for piecewise defined functions, first thing to note is the breakpoints of piecewise functions are always critical numbers. And again, by breakpoints, we refer to where the domain splits up. In this case, the breakpoints of this piecewise function are -1 and 3. So keeping in mind they're going to be critical numbers, so they have to go on our number line either way. What we had, it's important though, to see if they could be a min or a max, is to determine if the function is continuous or not at each breakpoint. And the way we do that is comparing the left and right hand limits. So let's find the limit as x approaches -1 to the left. So from the left, you would use, this is the left of -1. You use this top piece, you substitute -1 there, so it'll be -1 plus 3 squared. -1 plus 3 is 2. 2 squared gives you 4. So from the left, that's x approaching -1. The limit is 4. And then let's compare that with the limit as x approaches -1 to the right. For the right of -1, you use this middle piece, so that'd be -2 times -1 plus 2. Well, that would end up being -2 times -1 is 4. Sorry, it's 2. I'm ahead of myself. That's 2, and then when you add the 2, you get 4. So because those are the same, that means on the left and the right it approaches the same y value, so then we know that f is continuous at x equals -1. And that's important because if it's continuous, that means it could potentially be a relative minimum or maximum, possibly. Now let's find a limit from the left and right of our other breakpoint 3. So limit as x approaches 3 from the left, you use this piece here. So it'd be -2 times 3 plus 2. -2 times 3 is -6 plus 2 gives you -4. And let's find the limit as x approaches 3 from the right. Well, 3 from the right, use the bottom piece as the right of 3. So that'd be -3 cubed plus 12 times 3 squared. Well, that's -27, 3 cubed. Negative stays out front. And let's see, that's 3 squared is 9 times 12 is, let's see, 90 plus 18, so 108. Minus 27 gives you 81. So here you can see these are not even close to the same, they're not the same. So this tells us that f is not continuous at x equals 3. So both of these are going to go on the number line, but since the function is not continuous at 3, 3 is not going to be a relative minimum regardless. But it is continuous at -1, so it could potentially be a relative minimum. So now what we do is we take the derivative of our piecewise function. Just take the derivative of each piece. So the derivative of the top piece, using the chain rule there, the function side, using the power on the outside, that would be 2x plus 3 to the first, but the derivative inside is just 1. That applies, oops, I forgot to add the word 4 here. 4, x is less than -1. And then on the middle piece, the derivative is just -2. That applies 4. And what I'm going to do is drop off any or equal to's when I take the derivative of a piecewise function. So -1 is less than x, just less than 3. The reason why is if you put the equal to there, that means the derivative exists and it equals -2, which it might, but we don't know that, and usually it doesn't. And we can see that. Usually we have a corner even if it's continuous, so we can see that by plugging, if we plugged in -1 here, that would give you 2 times 2 is 4, which is not the same as -2, so the slopes, even though the original function does meet up here, the y values are equal, the slopes are not equal, creating a corner, so that's why I took the equal to off, because it's not differentiable at the breakpoint of -1. And then if we take the derivative of the last piece, that'd be -3x squared plus 24x. That applies for x is greater than 3. Again, I dropped off the equal to. You can see if you plug in 3 in here, that's not going to give you -2. So it's not differentiable at 3. And even if they were equal, in this case, we already know it's not continuous at 3, so it can't be differentiable. All right, now to find our critical numbers, we want to look at each piece and see where it's 0 or undefined. In this case, none of them have a denominator, so I don't have to worry about where it's undefined. We set the top one equal to 0, in this case x plus 3, the top piece, you get x equals -2. However, you got to be careful. You just have to make sure that that critical number actually would apply to that piece of the function. So let's check. -3, is -3 less than -1? It is. So that means you would use -3 on this piece of the function. So that is our first critical number besides our breakpoints. The middle piece is just -2. Well, -2, that'll never equal 0. So that's not going to give us any critical numbers. It's just a constant. And then the last piece, if we set -3x squared plus 24x equals 0, to solve that, we could factor it. It's probably easier to take out a -3x actually than just a 3x. That'll leave you with x minus 8. And when you set those equal to 0, either x equals 0 or x equals 8. So it looks like we have two more critical numbers. However, always make sure on these piecewise functions that you would actually use that piece of the function for those critical numbers. For x equals 0, is 0 greater than 3? It's not. If we plugged in 0 into the derivative, we would use this middle piece, not this third piece we just got. So because of that, it doesn't apply to that interval. 0 is actually not a critical number. So let's check 8. Is 8 greater than 3? Yes, it is. So 8 would apply to this piece. So 8 is a critical number. So our critical numbers are -3, 8, and our breakpoints of -1 and 3. So let's put all those on the number line. Put them down in order. So we've got, first one we did is -3, right? And then -1, and then 3, and then 8. And let's label our number line. This is f prime of x. So -3 and 8 made the derivative 0. And -1 and 3 came from our breakpoints where we had corners or it wasn't even continuous. So those would be the derivative would be undefined or does not exist. And let's make a note at the top of those breakpoints here, so we don't forget. At -1 that we found was continuous. So -1 with a little CONT for continuous. And at 3 we found the function was not continuous. So that'll remind us whether these could potentially be relative ends or maximums. So we can test -4 here. -4. Now the only thing you have to be careful of on the derivative when you're testing is make sure you use the right piece again. So -4 would apply in this interval. It's less than -1, so you test -4 there. -4 plus 3, that's negative. In between -3 and -1, you can test -2. -2 is also less than -1. You use this piece, but -2 plus 3, that's positive. In this interval, you can test 0. And for 0 is between -1 and 3, so you use this piece, but there's nothing to plug into. It's always -2, so it's always negative. Anything we plug in on that interval. And then between 3 and 8, that's 4. And 4 is greater than 3, so we use bottom piece. It's probably easier rather than using this to use the factored form. We test 4 into this piece, 4 times -2, that's going to be negative. 4 minus 8, negative. Negative times negative is positive. And then if we test 9 times -3, that'd be negative. 9 minus 8, positive. Negative times a positive is negative. So then let's see what this tells us about f of x. F of x would be decreasing, increasing, decreasing, increasing, and back to decreasing. And then let's go ahead and test, let's write down our intervals when it's increasing. We can say f is increasing on -3 to -1, using with 3 to 8. And f is decreasing on negative infinity to -3. And we have 1 to 3, so -1 to 3, and using with 8 to infinity. And finally, let's look at our critical numbers and see if they're relative mins or maxes, or neither. So -3 First order change from negative to positive, so that's decreasing, increasing, that's a relative minimum. At -1, first order change from positive, negative, increasing to decreasing, so that's a relative max because it's continuous. That means it could be. But 3, it changes from negative to positive, first order, so it goes from decreasing to increasing, so it looks like a relative minimum. However, remember, this is where it's important we figured out it was not continuous at 3. So even though it goes from decreasing to increasing, since it's not even continuous, it's not a relative minimum. And then 8, function changes from positive to negative, increasing to decreasing, that's a relative max. So what this would look like at 3, roughly, we notice the left-hand limit was -4 and the right-hand limit was 81. So the function does go decreasing, and then on the right it's 81, then it's increasing. But because they're not connected like that, that's why it's not considered a relative minimum. It's not continuous. So that's why it's important to first figure out its breakpoints and continuous. All right, so finally, let's write down the x coordinates of our relative extrema there. Local minimum, local max. So we can say f has a local minimum at x equals -3, and f has local maximums at x equals -1 and x equals 8. And that concludes the notes for AP Calculus on the topic of relative and local extremas for special functions, trig functions, and piecewise functions.